we Fourier transform the term everything kinetic and potential energy, and I got rid of all Hubbard interactions, leaving only exchange interaction. And you see the reason was just due to the fact that I can ignore one term was like u minus j. I can say that u is of the order of j, and then I can say that I can forbid hoping an interaction between two different orbitals. So focusing on the model, which is one of the possible models too. There is always competition between Coulomb and exchange interaction, and in principle, Coulomb interaction is always bigger than exchange. But if I did that, if for some reasons the matrix elements which have been defined and erased from the background before tells me that this is a leading contribution, I am arrived at
the specific spin configuration analysis is approximation or exact?
Well, no. This is also u. You know, the way I this is also the order of u. Everything is of the order of u. I just wrote a specific configuration associated with this scattering. Basically, this is the same Hamiltonian. If you Fourier transform your Hubbard model, you will come to this Hamiltonian in Fourier space. What was written before is T A n plus g to n, and here it was u sum over n up, n down. Each of them is a dagger n up, a n up, and this is a dagger n down, a n down. If I Fourier transform this Hamiltonian, I'm back to simple model without orbitals. I will get that. You see that this is because n down Fourier transform as function of u is equal to sum over k, a dagger k minus q down, a k down. And this is precisely this term. And the same n down q is sum over k prime, a dagger k prime, plus or minus q is very symmetric, up. So sorry, here it's up, and here it's down, a k prime down. So this is how I come to this derivation, and u doesn't depend on k. This is just one interaction. It doesn't depend on coordinate.
So we remove the double counting of sigma due to.
Yes. I wrote explicitly this way because you also notice that there are two terms, this and that, but since they are all the same and densities commute, I can write it just by the factor of 2. Adding summation. So what I'm saying is that being back to Hubbard model and writing in the momentum space, I can also be back to expression for susceptibility defined through the Linford function. So this function over q over 2kf, as I said, was equal to 1 plus 1 minus x, which is equal to x squared over 2x log 1 plus x, 1 minus x in 3D. And what I see here, let me put this now in this model. What I see here is that if I consider my function at q equal to 0, And at q equal to 0, this is just density of states. So chi node is equal to density of states as a Fermi energy times the Hilbert function over q over 2kf. And this is x. This is how Hilbert function looks like in 3D. You will have a tutorial devoted to calculation of Hilbert function in dimensions 2, 3, and 1, 1 to 3. You will derive this formula, and this is actually a very simple calculation, but I don't want to spend time for that. What one can see that this susceptibility becomes unstable. This susceptibility divergent when u times density of states is equal to 1. And this is also magnetic instability in itinerant strongly correlated systems. What we see from the expression for susceptibility is that 1 equal to u times density of state is special point. If u times density of state is smaller than 1, then the system is paramagnetic. When it is larger than 1, the system is ferromagnetic. And this is so-called Stoner criterion. And the magnetism is Stoner magnetism, which tells us that the instability occurs when the losses in kinetic energy becomes comparable with the gain of potential energy. So kinetic energy, the density of state is one of the Fermi energy. So when gain in potential energy becomes bigger, U is bigger than 1 over density of state, system there is a phase transition in the system, and this phase transition is into magnetic state. So you see that this strongly correlated model, which is Hubbard model, can describe you variety of transitions. Namely, at half filling, it describes metal insulated transition. At the same time, this metal insulated transition is related to magnetic transition into antiferromagnetic phase. However, at some filling different from half filling and strong enough Coulomb interaction, the system is rather ferromagnetic if the Stoner criterion is satisfied. Let me now plot this susceptibility chi node as a function of Q, which is basically a Hilbert function. We discussed it yesterday a little bit. So this is F as a function of Q, and this is 2K F. And this is 1. So this is how Hilbert function looks like in three-dimensional case. There is an inflection point where derivative becomes infinite, which tells us that there are some oscillations which we associated with this RTQY interaction when we discussed indirect exchange. But there are no any instability associated with momentum transfer equal to P-Fermi moment. If we plot the same Carter function for two-dimensional case, it will look like that. So the singularity on 2kF is weak singularity, it's just kink. So So this is 2D, this is 3D, but you see that the singularity has a tendency to increase when we come from high dimension to low dimension. If we plot the same curve for one-dimensional case, we will have logarithmic singularity on 2K. I'm not going to give you a formula for 2 and 3 dimensional, 2 and 1 dimensional case, because we will discuss it in one of your tutorials. But what I'm saying to you here is all the same. When you come to system with reduced dimension, you have more possibilities to for instabilities, which increase with decreasing of dimension. And actually, this indicates that in one-dimensional situation, any kind of instability can occur. On one hand, namely instability associated with a ferromagnetic transition, if you are above total criterion, but also anti-ferromagnetic transition. This will tell you that the susceptibility has instability not only at Q equal to 0, but also at finite Q associated with 2KF. But in one-dimensional systems, oscillations are so strong that they are not in favor of any kind of instability. They will destroy any instability, whether it's superconducting or magnetic or whatever. What did we see here? We see that all systems 1, 2, 3 can facilitate external instability if this criterion satisfied. However, in one-dimensional system, there is additional instability occurring to the wave vector 2KF, which is rather antiferromagnetic, because we know that in antiferromagnets, the instability occurs in local antiferromagnet on the reciprocal vector. Here, we have instability associated with the interlacerate vector, the vector which is associated with momentum transfer through the Fermi surface. Okay, so summarizing, what did we learn from the Hubbard model is the possibility to have a metal insulated transition and two types of magnetic transition if the system is in reduced dimension. Actually, the antiferromagnetic instability in 1D, which can be seen as a cartoon, is a kind of spin density wave. So you have spins being down, and then spins being up, and this vector which characterizes the modulation of spin density is just twice the phenomenon. It doesn't have anything to do with the lattice structure, because we are talking about electron gas subject to tight binding model with a Coulomb interaction. This is what you can find in literature as spin density wave. And this is a kind of analogous to antiferromagnet, but this is not local. You really have a modulation of spin density of electrons, which are itinerant electrons, are not associated with lattice structure. Let's now spend a few words for discussion of Anderson model. Any question? Or it's too complicated? Tell me.
Yeah, it's too complicated. Can we solve some problems so that obtains all the elementary things and the case?
You want to have a book on that? Look, if you take any old-fashioned book like Simon or Kittel, which are very good for studying the basics of many-body physics, you will probably not find a focus on this theory. Take any modern book For example, book of Auerbach. Auerbach. Which is called, I think it's also called something like quantum magnetism. I need to check. There is Japanese book Moria. Which is called spin system with a collective modes. I will give you an exact reference to that tomorrow, which are concentrated on this itinerant, strongly correlated models based on Harvard method. I should say that real systems like iron or cobalt or nickel rather belong to class where the Coulomb interaction is of the order of kinetic energy. So the matrix element of Coulomb interaction is of the same order as matrix element which describes hopping of electrons, which makes construction of theory very difficult because you don't have a small parameter in the system. I try to show you that when interaction itself can be regarded as a small parameter, one can proceed with a perturbation theory taking interaction as element of perturbation. On the other hand, if one has a kinetic energy much smaller than Coulomb interaction, matrix element of Coulomb interaction, then one can start with on-site quantum mechanics, calculate wave function from atomic physics, plug it into the crystalline lattice, calculate Hoppen's matrix element for the overlap of this wave function, and proceed treating kinetic energy, namely Hoppen, as a perturbation. This is another option. But if you are in between, namely if your Coulomb and kinetic energy are the same, then one needs to proceed with some powerful methods like density functional theory, which you probably learned a bit from Professor Bauer lectures, or thought about them, or do molecular dynamics calculations, or do some cluster approximations based on mean field theories, dynamical mean field theories, or other modern methods like density matrix renormalization group, for example. These are modern tools. Local density approximation is a kind of density functional theory. Local density approximation, which takes into account U, which is called LDA plus U, and all other types. I'm personally not an expert in doing numerics for strongly correlated systems, but there are plenty of systems which are good for some system but fail for another system, but at least there is a good starting point for description of strong correlation. And people are working on this. This is one of also fields which grows and develops quite fast because it is very demanding. As I said, the hope to find description for high temperature superconductivity and fermion puzzle is associated with a hope to resolve description of strongly correlated system on a reliable way, so the theory can not only describe system but to have some predictive power. Okay, look, I understand that it's difficult for you to follow, but on the other hand, you are here for 1 year to take this special course and special courses, and my feeling is that in addition to basic knowledges, which you also should work yourself to improve, you need to get knowledges of what's going on in modern physics now. What are the models, what are the theories, and what are the open questions? Because teaching you something which was well known 50 years ago is of course very important and necessary part of my work. And I try to explain you basic things associated with symmetry, basic physics, things associated with spontaneous breaking of this symmetry, but also would like to show you that systems are usually not as simple as one can imagine discussing quickly interactive models, some rotations. The physics is more complicated, and this is again probably your niche where you can do something, you can contribute to this research if you like to continue to work in independent method theory. And this is also if you think about doing some PhD program somewhere, this is probably one of the fields where you can work quite efficiently. I said you that ultra-cold gases and the physics of fermionic and bosonic gases in optical lattices and magneto-optical trap is one of the hottest topics of modern condensed matter physics now. Many groups work with these ultra-cold gases experimentally and theoretically, and the goal, or one of the goals of this group, is to model this strongly correlated behavior in order to be able, if not to calculate, since model is complicated, but to measure with the optical lattice experiment the correlated function for the Hubbard model, for example, for the Anderson model, and by measuring these correlation functions in almost ideal setup, because everything is highly controllable in this optical lattice experiment, one can give an answer on the phase diagram on the kind of instabilities which occur in the system, and what is the most preferable stability, since you see that in all this system, phase diagram is very much complicated. Many different orders compete with each other. Namely, the system can be superconducting, or magnetic with antiferromagnetic transition, or magnetic with a ferromagnetic transition. Then there is a possibility of coexistence between superconductivity and magnetism. Then there is a low-dimensional ingredient which tells you that the fluctuations are strong and they destroy long-range orders. So all these ingredients make physics not simple at all, but still very, very interesting, and hopefully we will see solution of few models one or another day. Okay. Now, let me say a few words for Anderson. Let's consider two subsystems that we have band. For example, we have a conduction electrons which contribute to conduction band, and we have deep orbitals which is far away from the Fermi level. So this is energy, this is thermal energy, and this is the position of level associated with the deep atomic levels very far below thermostat. And let's write a simple Hamiltonian which will describe position of this d level, d dagger and sigma, d and sigma. So these are deep orbitals, localized electrons. They cannot move because they are far away from the thermal surface. Then, as I said, there are conduction electrons. So these are C electrons, conduction electrons, and let's write the possibility for some of K and sigma V K D and sigma C K plus complex conjugate. So what is written here is the possibility of conversion of the electron being far below Fermi surface to C electron, so kind of hybridization between C and D electrons. So the electron from the orbital can go to the Fermi surface and other way around. So this is Anderson model. Of course, if you add Hubbard interaction on each side, then we will have a mixture of localized physics and itinerant physics with the possibility of this conversion. But let's first not do that. Let's look at this Hamiltonian, which looks like very simple. It looks like quadratic, so one can diagonalize it. And if we exclude the single occupancy of the electrons on inner shell, we can do it through different ways. There are unitary transformations which allow you to do it directly. Then you arrive at the Hamiltonian, which is nothing but on the model where J is equal to Vk prime over half 1 over epsilon k minus epsilon d. Let me store here its energy of level minus if I add down u plus epsilon d minus epsilon. So you see that the model which describes some atoms with atomic levels and conduction band and interaction between conduction electrons and localized levels is generic for the Kondo model, where the interaction of spins of conduction electron with a spin impurity or spin coming from inner shell in a lattice can be derived. As I said, this model being generic for Kondo effect is also important for strongly correlated physics. This is known as the Anderson model, and I will discuss the properties of this model in more detail when we discuss quantum dots in facultative lectures, because this model is also generic for describing the transfer from the leads to the localized model, which is a quantum dot, and the effect which can occur in the process of this quantum transfer in this lens. What I wanted to tell you about Anderson model is to show that this Anderson model can lead to Kondo model, provided that the interaction is antiferromagnetic, so you have a competition of these two terms, and this level is sufficiently far away from the Fermi surface. Of course, we can assume that D level is close to Fermi surface, then the system corresponds to description of so-called intermediate valency system or system with valence fluctuations. This is another story about another class of strongly correlated systems. Many of systems containing transition metals in it possess this intermediate valency property. So Anderson model is not only generic for Conde effect, but also describes some other strongly correlated effects in the systems. Okay. Questions? If not, on Thursday we discuss some non-phonon theories of high-temperature superconductors, conductors, and next week we proceed with disordered system, namely Anderson localization, weak localization, and little discussion of system with Coulomb interaction, namely excitations in electron-ion plasma. And tutorials will be next week on Monday, or not Monday, Tuesday. After Easter, I give you homework, which we discussed just after, before exam. I will collect it a few days before exam. We spent one extra lecture, not lecture, extra meeting, which will take place before exam, just for discussion of homework and problems, as well as organizing problem for exam, and tutorials which Gunesh will give to you in my absence will be devoted to green functions of Bloch equation and Schrödinger equation and calculation of different functions in a given equation. By the way, did you succeed to solve the Bloch equation with the full 3 terms? No? Did you try? No, it's interesting because the deceiving fact that it really looks like linear, but try it. You will see that it's not at all the case. The fact that your function comes linearly into equation doesn't necessarily mean that when you exclude all other functions and write down the equation for a single function, it will be linear equation. Because in the process of exclusion, for example, you can solve some auxiliary equation which will give you nonlinear functions like exponent or sine or cosine, and resulting equation for single functions can be highly nonlinear at the end of the derivation. But it's forced time. Okay, good. So, Steve,
From this one?
Yes.
I don't like short.
Why you don't like it?
For me, it's not interesting.
Really?
And I don't need to.
Even as you don't like analysis, but it's the majority. This you have only one, yes? As is everything. And apple.
Even the algebra is for me, it's more useful.
Yeah. It's good to learn. It's good to learn.
Where is the question? Where?
You want?
Huh?
You want?
No. It's today.